Good morning, good afternoon, and good evening. First of all, I would like to thanks to the organizers for permitting me to give this talk. This talk was done, the work research of this talk was done in collaboration with people from France, from Belgium, and two PhD students in Buenos Aires. The talk of today will speak about the quantification of the magnetic twist distribution inside magnetic clouds. And this is very important to can link the solar and interplanetary events. Before starting to present our study itself, I will revise a bit the state of the art and difficulties associated with this kind of studies. Main properties of flux ropes can be scalars: density, pressure, intensity of modulus of magnetic field, modulus of the velocity, temperature, plasma beta. But also can be quantities associated with vectors. For instance, the axis direction of the flux rope, the magnetic field with the three components in the flux rope frame, the twist, fluxes, magnetic fluxes, and magnetic helicity, among others. So due to that, the meaning of the components of vector emerge in the magnetic flux rope frame, and due to the difficulties of getting this real orientation in the flux rope axis, scalars are much more robust, but vector need to be carefully computed to can proceed with physical interpretation. So that to get the twisted flux tube or flux rope orientation as accurate as possible, several critical issues need to be considered. But this is not an easy task, even in the most simplified models. For instance, if we get a very simple cylindrical flux rope cross-section, it is critical to correctly transform in situ observations of vector physical quantities to the flux rope local orientation, and that get these quantities. So the axial and the azimuthal components of the magnetic flux in the proper frame. Major quantities depend on the local components. For instance, as I said, magnetic fluxes, magnetic helicity, and the distribution of the magnetic field. Thus, these two quantities are key, in particular because these two quantities determine the twist distribution. R is the distance to the axis of the flux rope, and the twist is the amount of the angle that rotates the magnetic field per unit length along the axis, Z. But you can notice that the twist has a singularity because R similar to 0 is the value when we go to the axis, near the axis. So it has an avoidable singularity as the origin. Due to that, B phi also tends to 0. And if it is a linear trend of B phi to 0, as expected from most of the models, the singularity can be avoided, getting the twist at the origin as a non-infinite number. But however, a small error and a small mistake that we can obtain in the orientation of the flux rope will couple these two components and will be not possible to avoid this singularity as an artifact of the method. So this is very important and very crucial to can get a proper orientation. So by another hand, entering deeper on the orientation of the flux rope, let me revise a recent result of Demoulin et al., where we show that the most appropriated angles to describe the flux rope structures and the orientation in the solar wind are lambda and I, and not theta and phi as typically used from the 80s. The main reasons for choosing these angles are because the spherical coordinates has an illness near the poles. Thus, it is better to define x GSE as the polar axis, because this axis will be no parallel in the real magnetic clouds to x GSE, and that we will not find axis of flux ropes near this illness of the method of the angles. Another reason to obtain or to work with these angles, I and lambda, is that rotation of each of these angles are strongly associated with the symmetries presented in magnetic clouds, because Bx and Bz in the flux rope frame are symmetric, present symmetric profiles, while By present an anti-symmetric profile. Then to combine the two angles will modify the two symmetries. But if you choose only variation of one of the two angles, will preserve this symmetry. And this is very important. You can enter deeper on the details in this paper. And then our conclusion is that these two angles are a kind of normal modes as a comparison with dynamical systems in the term of the two motions are uncoupled with this using these angles. So we use these angles and we show some examples here of a method to obtain the orientation of the flux rope using synthetic magnetic clouds, synthetic flux ropes, Lundquist flux ropes. And in particular, we played in that paper with different cross sections. B over A equal to 1 means a cylindrical cross section. We also permitted expansion and compression. Zeta is the parameter, meaning implying this expansion, which is positive, and negative is the compression. And 0, which is the case shown in this figure, means non-expansion and non-compression at all. And also, we analyzed different impact parameters, which are the distance, the minimum distance between the trajectory of the spacecraft and the axis of the flux rope. Then what we can see in this figure is that applying the method that we call minimum variance 0, which is minimum variance applied to the direct magnetic field observations, or magnetic variance 1, which is magnetic variance applied to the normalized magnetic field. In each time we normalize by the modulus of the field, so we get only the orientation of the magnetic field in MV1. And we compare here the error that this method obtained in each of the three axes, X, Y, and Z of the flux rope, and also the error obtained in I and lambda. And as you observe, I, when we apply minimum variance 0, and also when we apply minimum variance 1, is the mistake delta I, the mistake of the angle Y is 0, even for impact parameter very large. However, according with the impact parameter is a bit larger, we start to departure from the ideal orientation, and we introduce a bias of the order of 10, of the order of 5, when we approach to 0.3, 0.4 of the value of the impact parameter. So summarizing, if we use this method to obtain the orientation of the flux rope, and we use cases with not strong asymmetric BT, because we tested for symmetric cases, and with cases of parameter, because we don't want to go with delta lambda huge, so we needed to be very close to 0 of delta lambda. So if we are in this circle, so impact parameter lower than 0.4, we get uncertainties only on lambda and less than 5 degrees, which is pretty nice. So in order to quantify the asymmetry of the profile of the magnetic field, we can compute this parameter, which is a kind of center of mass, but applied to the magnetic field intensity. These are three examples. This example presents a strongly magnetic field in the front and weaker in the rear. This presents the opposite, and this presents a pretty much symmetric case. So we want to keep these cases, and then in a quantitative way, we will analyze this parameter CB in order to decide if the profile is symmetric or asymmetric. And then this is the histogram of CB, which shows that in our sample, which is based on observations of wind, and this period of time, and using the catalog of Lepin, only considering quality 1 and quality 2, and also filtering by the symmetries using this parameter in such way that CB modulus is lower than 0.1, which is inside this range of CB. Also, we observe a lot of impact parameter in this sample, so we also restrict to impact parameter lower than 0.3, sorry, and then this is the filtering that we use, and we obtain a sample of 25 magnetic cloud, which we call QBest. And then we apply to this sample the superposed epoch method, which is a method very robust because this method is reinforcing the common properties of every event and tend to kill peculiarities of specific events. This method rescales the profile in the range of interest and define bins, and for a given event, define the profile in these bins, and then average all the events. And then we obtain a typical average profile. And this is the result. This is the result of the magnetic field intensity, Bx, By, and Bz, the three components in the flux rope frame. And then for the first time, we present this typical profile of very well-behaved magnetic clouds in the solar wind. You can observe here By, this is the typical profile of By, negative change in the sign, and Bz. And this is a comparison of two models, observations with two models, with the Lundquist and with Goldhoel. And there are very good agreement with both models with the observations. And also using these formulas for getting the twist profile, but considering all these specific cases which are well behaved and we can trust on the orientation of the flux rope, we'd obtain the twist profile inside the flux rope from this superposed epoch. And if we use this expression, so we observe without considering the impact parameter and we approach to zero, we don't avoid the singularity, and we obtain this increase, this strong increase near the axis. But considering the impact parameter and all the properties and the features that we shown before, we can observe in the proper frame of the flux rope using cylindrical components this profile. And this singularity was avoided and is not present here. And the profile of the twist, which starts from a value of 10, which means 10 turns per 1 AU, so per 10 turns from the Earth to the Sun in the flux rope. And in the border, in the boundary of the flux rope, is increasing the twist. So start from this value nearly constant and increase to the border, reaching up to 25 turns per 1 AU. So this is summarizing in this. So for summarize and conclude this talk, very fast, physical and geometrical properties of interplanetary flux rope are crucial to link them with their potential solar size to better understand physical mechanisms in the solar wind and to improve space weather forecast. So I will keep this conclusion because lack of time, but I just mentioned the most important, which is that the typical magnetic structure obtained from superposed epoch analysis method is more consistent with the Lundquist profile than with the Goldhoel configuration, which means a twist constants along the distance from the axis to the boundary. Thank you very much for your attention and have a good meeting in this virtual mode. Thank you very much for your attention.